Okay, so as you just saw in that screenshot of the simulation, when a single wave pulse, this is the upper picture here, the upper picture is a single wave pulse. And it's really important to understand that this is a disturbance, right? What that is right there is a disturbance, in this case, in a tight string. Right, so you give it a quick flick of the wrist. Say you give a slinky a quick flick of the wrist, and a disturbance travels down the slinky. Well, what you have is a single wave pulse. Okay, and really the takeaway from this is that it has velocity. It is moving. This disturbance does move. It can do work. It can push on things and pull on them up and down. But another really important thing is that red dot right there, that red dot, when the wave disturbance gets to that red dot goes, first it's going to go down, and then it's going to go up, and then it's going to be right back to where it started from. So the straight lines here are the equilibrium position of, say, this rope that is tight, or the slinky that is tight, and that's the equilibrium position, are the straight flat parts, and then the disturbed position is the wave pulse itself. Now, if this happens continually, as in the bottom picture down there, we call that a continuous wave. And basically, the yellow line there. So let's pretend this is a water wave, right? So the yellow line would represent the level of the ocean water, say, when it's very calm out. But if a disturbance is caused at sea by, say, wind, most waves are caused by wind. The disturbance travels, and the water is knocked out of equilibrium and oscillates back and forth through the equilibrium position. It goes upwards out of equilibrium, and then it falls back downwards through equilibrium, etc., so on and so forth. And you get what's called a traveling or a continuous wave. Now, let's be clear up here, the upper picture, that when the wave gets to the red dot, I'm going to switch colors here. When the wave gets to the red dot first will go down, and then it will go up. That's the actual motion of the particle. If you watched some little chunk of that wire or that slinky or whatever it is we're talking about up there, if you watched some small chunk of it, you would see those atoms move up and then move down and then go back to equilibrium as the disturbance passed by. But the wave speed itself, the disturbance is going this way. So this type of wave is called a transverse wave. Transverse, meaning that the displacement from equilibrium is up and down. That's displacement, right? But the velocity is 90 degrees, is perpendicular to that. There's the velocity vector. So they're transverse to each other. They're not in the same direction. The displacement and the velocity are at 90 degrees to each other. So that's called a transverse wave, and that's most of the waves most of the physical waves you've seen are transverse waves. All right, next page here. The next thing I'd like to cover is simply some wave anatomy, right? So here's just a kind of a zoom in of the previous wave, and let's go ahead and define some variables here. I'm going to use the Greek symbol lambda for wavelength, right? So let's define this as wavelength. Right? I wouldn't want to have to write all these letters every single time. Wavelength is lambda. I'm going to use a capital A for amplitude. And then I'll just label the other stuff as we get to it. This is called the origin. The yellow line is the origin. I just explained what that was a few moments ago. Or the equilibrium position. That's the rest position of the thing that's vibrating. Whether it's water, or a slinky, or a guitar string, or something like that, it has a rest position, and the rest position is referred to as the origin. The displacement from equilibrium, same as the SHM lesson not long ago, the displacement from equilibrium is called the amplitude, right? The amplitude is right there. And the wavelength, well, that's literally the length of the wave, right? So that's measured either from crest to crest. That's called a crest. That's called a crest. The top of the wave is called the crest. And the distance between that is some value. And if it's a water wave, it could be feet. It could be tens of feet. It could be even 100 feet or more. If it's a sound wave, it's much, much shorter, in the range of a meter or under that. And if it's a light wave, it's much, much shorter, in the range of nanometers, billionths of meters. But waves have length, that's called the wavelength. Waves have height, and that's called the amplitude. And just a quick aside here, sometimes when I'm looking, for instance, at the buoy reports to see how the surf is, if it says the waves are 3 feet high, I start to get quite excited. And that's not because the waves are going to come up to, say, my thigh or something like that. But a 3-foot wave, this orange value right here, that value right, that would be 3 feet. So if you're a surfer, you're surfing this wave. There I am, later today. There I am surfing a wave, and I'm going to zoom right down into the trough. By the way, that's called a trough, TROUGH, right? And up top, I didn't label it. It's called a crest. I did say it, but I didn't label it. The crests are the top of the waves. Right, so if you zoom from the crest down to the trough, and it's a 3-foot wave, well, that's actually a head-high wave for me, because it's going to be 3 feet from here to here, and it's going to be another 3 feet from here to here. So a 3-foot wave, to somebody standing in the wave itself, looks and feels and smells a lot like it's 6 feet high. So that's why surfers start to get excited around the 3-foot mark. Not because the waves come up to our waists or lower or something like that, but because they come to head high. A 3-foot wave is a head high wave. Okay, so let's see, a little bit of wave anatomy here, just making sure I'm covering all my bases here. The other thing I wanted to cover, well, that's a particularly kind of silly wave here. Let me just get rid of that part over there. So if waves were passing you, let's just derive a quick little formula here. If waves were passing you, let's say you're standing by watching these waves. Maybe you're on this little pier. I'm going to draw a pier. So here's a pier, and you're standing on top of this thing. It's not going to fit on my screen here. But if you're standing up above that dot, watching the waves go by, if you estimated, let's say you estimated this. Oh, I don't know. That's about 2 of me long. So let's just call it 2 meters. Let's call it 4 meters. Just roughly. Let's say that you go down to the water and you look at the waves and you estimate the wavelength, or maybe you measure it somehow carefully. But let's say that's supposed to be a lambda up there. Lambda, that's lambda right there. Right. So let's say lambda is 4 meters, whether by estimation or measurement. You said that the waves are about 4 meters apart. And let's make this nice and easy. Let's say you bust out your stopwatch, and so when this part of the wave gets to here, I'm going to make a red dot. When the crest of this wave gets to you, you start your watch, and it passes underneath your position here. It passes underneath you, and you start your watch, and then, I don't know, let's just make the math super easy. 8 seconds later, that part passes you, right? So you would say, oh, well, 4 meters of wave, here to here is 4 meters of wave, just went by and has got a period of about 8 seconds. How fast do you think it's going? Well, let's see. It went 4 meters in 8 seconds. I bet just about every one of you is saying, oh, well, if it went 4 meters in 8 seconds, the velocity must be about 4/8 of a meter per second, about half a meter per second. And you would be correct. That would be true. If 4 meters of stuff goes past you in 8 seconds, that wave is traveling at a half a meter per second. So what did you just do? Well, you just did wavelength divided by period. Wavelength divided by period. So this is true. Velocity is wavelength over period. But it's more often, this formula is more often seen like this. Wavelength over, what's period? Oh, it's 1 over frequency. Right, so 1 over frequency, that's a 1 over f, sorry about that. And so let's multiply by the reciprocal here, and we get a formula that's very common in wave mechanics and wave motion, which is it's going to be wavelength times wavelength divided by 1 over f, which is the same thing as wavelength times frequency. So there's a nice simple formula for you. Velocity of a wave is its wavelength times its frequency. Or its wavelength divided by its period. Either one of those are valid. Okay, I'm now going to switch to a quick video from YouTube on longitudinal versus transverse waves. That should just take about a minute, and then I'm going to carry on here. Hold on.
In a longitudinal wave, the disturbance that makes up the wave is along the direction in which the wave travels. Longitudinal waves are also referred to as compression waves. In a transverse wave, the disturbance that makes up the wave is perpendicular to the direction in which the wave travels.
Okay, so how fast do transverse waves go? We just said very recently that the velocity of a transverse wave is wavelength over period, which is the same thing as wavelength times frequency. That's a general formula. Now, if this wave is in a spring or anything under tension, like a wire, a cable, a guitar string, any wire under tension, any string under tension, then the speed is velocity is equal to the square root of the force of tension over the linear, the mass density, the m per L. We ran into some m per L recently when we did cat on a plank. So this lower formula is the speed or the velocity of a wave. Velocity of a wave. That's an E there. Velocity of a wave in a material under tension. Under tension. So this one applies to as I just said, strings, cables, anything being pulled tight, slinkies, etc. If see if it makes sense. The tighter you pull it, the more force of tension there is, the higher the velocity. But if it's got more mass per length, if it's got more inertia, if it's harder to move, the m per L is higher, then the velocity is lower. Right? That makes sense to me on an intuitive level. So those are two formulae that you'll run into for speed of transverse waves, the up and down waves. Okay guys, here we are with a simulation on PhET. I'm going to switch this to pulse right here, and I can send a quick pulse into this string that's under tension. Now you notice it dies away pretty quickly because it's somewhat realistic. With the damping turned up a little bit, we can idealize the situation and turn the damping all the way down. So damping is basically energy loss due to the stretching and heating of the thing that's vibrating. So if it stretches and vibrates a lot, there's a lot of energy loss, and the thing dies out quite quickly. And if there's ideally, if there's zero damping, which doesn't happen in the physical world, we can keep it going for forever if there's no friction. So there's a single upward pulse. I gave it a single upward pulse, and it's traveling back and forth. And this is interesting stuff. So this is a transverse wave moving up and down. If you watch any one of these green particles, its entire motion is up and down. It goes up and it goes down. It's pretty clear that this green dot right where my cursor is not moving from point A to point B and point A and point B and back and forth again. It's just going up and down. So the motion of the medium is transverse. It's perpendicular to the motion of the wave. The motion of the wave is left and right, but the medium is only up and down. So what is this thing that we're looking at? Well, it's a disturbance. It's not a physical object at all. It's a disturbance within some sort of a medium, in this case a spring, or a string, or a cable, or a cord, or something like that. Now, as we turn up, the tension is pretty high. If I turn down the tension, we see the thing slows down. And if we tighten it up, it goes faster. And you musicians know this, right? When your violin string is flat, you tighten it up, and it vibrates more quickly, and you hear a higher frequency. And if your guitar string is sharp, well then you can lower the tension in the guitar string, and it doesn't vibrate as quickly, and it maybe goes into tune. Right? So this is a transverse wave, and the big point I wanted to make today was that it's got a speed that is a function of its mass, its linear density. You know, if this is super heavy, it's going to go slower, and if it's less massive, like a fishing wire or something like that, it's going to go more quickly. But tension is the other main factor. High tension, faster; low tension, lower. It's really too bad we're not in class. I've got great activities that I developed when I was in grad school to play with slinkies in the hallway and time the stuff and discover it in an inquiry-based fashion. And it's kind of bums me out that you guys don't get to play with slinkies in the hallway and create waves. It's super fun, and I don't know. It's really cool and valid, and it gives good results. And this time around, we're going to have to be happy with simulations. All right, but let's tune in back to the rest of the video, and we will take it from there. The speed of a longitudinal wave, though. So let me just write this down for you. For a full and detailed explanation for the speed of longitudinal waves, I would go to page 304 in your textbook, but I can summarize it right here. If it's in a solid, the velocity is the square root of what is commonly called the elastic force factor. So elastic, I'm going to be extra messy here, elastic force factor, that is basically a measurement of how shall I say this, how incompressible it is, how squishy it is not. Let me say more on that in just a second. Elastic force factor over inertia. Right, inertia comes from the mass per volume, so the density, and the elastic force factor is a measurement of something sort of, I don't know how to say it simply, how stiff it is, how rigid it is, right? So if something is very rigid, like steel is very rigid, and so sound travels really well through things that don't go too far out of equilibrium when you give them a hit. It goes much faster through, say steel, and I don't know, another extreme, the other end would be elastic force factor of something like a swim noodle. The elastic force factor of a swim noodle is very low. It's very squishy. So elastic force factor is sort of 1 over squishiness. I don't know. That's not very official now, is it? But if something's very squishy, you can imagine that sound waves or vibrations won't travel very well through it if something's very squishy. If you whack one end of a swim noodle, the other end doesn't really get too much energy, and the waves, the disturbance doesn't travel too quickly through it. Each particle takes a long time to squish back and forth. A lot of energy gets lost because of all the motion. But if you have another, the other extreme I mentioned a moment ago would be something like steel. If you give a steel rod a whack on one end, then it doesn't compress much, and that vibration travels really quickly because there's not much back and forth between those atoms or molecules. And this one's density. So the other way to write this equation, this is all on page 304, as I just said, but this is often written as velocity. So if it's in a solid, if it's a longitudinal wave and it's in a solid, it's the square root of the elastic force factor, which is E, sometimes Y for Young's modulus, but E over density, which we signify with rho. So this is if it's in a solid, steel or iron or something like that. So this is speed of a very important longitudinal wave in a solid. And if it's in a liquid or a gas, the formula is basically the same, except it's not. We've got a different type of measurement because if it's a liquid or a gas, the elastic force factor, the elastic force factor is referred to as something. It's called bulk modulus, B over density. So if you're wondering about the speed of a wave in water, you do water's bulk modulus over its density. If you're wondering about the speed of a wave through air, you would do air's bulk modulus over density. But if you're wondering about steel, you'd go to this one over here. You'd do elastic modulus over density. And there's a table of very common bulk and elastic moduli back in section 9.5, chapter 9, section 5, I believe. Yeah, page 238. So you can find these bulk moduli and elastic moduli. There's a table on page 238. So page 238 for elastic and bulk moduli. Okay, that's what I'm going to say. Oh, one more thing here. Be careful. If the question is about salt water, oops, sorry, let me go back here. If the question is about salt water, the density is different than fresh water. Fresh water is 1,000 kgs per cubic meter, but salt water, although it does vary with latitude and temperature and things of this nature, salt water is generally taken to be about 1,025 kgs per cubic meter. So if the question says a fisherman's in the ocean, yada, 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 it's probably going to be using a density of 1,025. And if it's a lake or a river or something like that, you would use a density of fresh water. Okay, I hope this helps. More to come. And stay well, and I hope to see you guys soon. All right, take care.